Hello students, welcome to Unit 2. We are heading to Chapter 2 here, Unit 2. So in Unit 2, reaction mechanisms in the octahedral complexes. So first we'll deal with the energy profile diagrams. It's also called as reaction coordinate diagrams, which is derived from the PES, that is potential energy surface. Okay, computerized form of this deriving the energy profile, that is potential energy surfaces. Okay, so what is this reaction coordinate diagram? So we know that any reactant A, so it's a reaction of A giving product C. So reaction A is there. So when we have the reaction here, so go to form from product C here, from A to C. So you can see that it is going to some activation energy here. Okay, so this is activation energy. So this reactant has to pass this activation energy, then this product is going to form. So it depends on this activation energy, how fast the reactant is going to form the product. That's why we say that it's a statement that difference in energy between the reactants and the activated complex. Reactants and the activated complex is called activation energy. The difference should be less. If the difference is more, then the formation of the product will be more. And that's why we say that in the addition of the catalyst, so when we add the catalyst, what will happen, the this activation energy will be decreased like this, and we get the product here. So the difference in energy between now the activated complex others reactants is less here in the presence of the catalyst. So one more thing here, so we have to in the coordinate diagram, reaction coordinate diagram. So if the reactant starts from here, so this is a reactant and it goes like this activation energy, and after that it comes down and the product is formed here. So what will happen here? So while coming from the activated energy to formation of complex, there will be very liberation of the energy here. So like this, the energy is liberated. So such reaction we call it as a exothermic reaction. So we call it as a exothermic reaction. So a lot of energy is released here, and finally the molecule loses all the energy and comes to the loses the energy and forms the product. Is it right? So exothermic reaction, and it's most favorable type of reaction. So this is the most favorable because it is losing the energy and then finally coming to the product formation. Okay, so this is what in some cases what will happen. So we start with the reactant here A, and when we go like this, it will go to activation energy, and here it will going to form the product like this. Here it is not crossing this reactant. So if I go like this, it's not crossing the reactant. Here we are going to get the product here. So here what will happen to product is very fastly formed here with respect to the reactant here. That's why what it will do, it will absorb the energy now. So it will absorb the energy from the surrounding like this, and that's why this process we call it as a endothermic. This we call as a endothermic. See, and since it is absorbing the energy from the surrounding, so this type of this we call it as unfavorable. So this is a unfavorable mode of the reactions, we can say. So like this in the coordinate reactions coordinate diagram. So these three things we can justify here with this reaction coordinate diagram. Fine. So see, sometimes this is the case of the elementary reaction. This is a case of the elementary reaction which is having the step one. So in single step it is going to occur here. But in some cases you can find that the reactions have the multi steps reactions. Okay, so how the coordination reaction coordinate or energy profile can be drawn. So here we have drawn it, energy versus coordinate reaction. Okay, reaction coordinate, energy versus reaction coordinate. So you can see here this is a single interval, this is zero. Okay, so here a zero elementary step, so it's a single step, so no intermediate is going to form here. So in this case we have learned regarding exothermic, endothermic, and favorability, unfavorability. So here we are learning the single step. So intermediate is here. So when the intermediate is there, so this type of reaction coordinate diagram energy profile will be there. So where you see here, so I start with the reactant A. So here I get here two profiles, two activated complexes here to finally going to get the product here. So here this is the intermediate. So this is what, and always the first step is always slow. Okay, the first step is always slow. then finally the fast, and it is going to form the product like this. So this is one case is there. Okay, so you can see here another case. So first step you can see here is very fast here, and here it is slow because of this more activated here. So this case also is possible from reactant. Okay, so from reactant to get product. So this is slow, then fast, and product. Here you can see here this is fast, then slow, then the product here. So this case also will be a possibility here. So like this, in one case, in some cases there are two steps reaction mechanisms will be there, step 1, step 2. So here what we'll find, two intermediates are going to form here. See here, and these two intermediates can be in like this, how we saw here. So how before going to form the product. So here also we can see the three different intermediates. See here, so first from product, from reactant A to form the product C. Okay, to form the product C. So you can see here from A to C there are two steps is going to found here. So first step you can see is a bigger here. First step is very slow. Okay, then intermediate one is fast, almost this also same, then we are going to get the product. Okay, so this is what here in here this case you can see the intermediate can be like this in between. Okay, between the reactant and the product. So in between you can see it's very slow. So initially fast, and finally it is going to form the fast to get the product. But in here the initial mid place of this will be very slow. So intermediate. In some cases you can see here, see. So intermediate 1, 2 will be very fast here. So this is a reactant, and we are getting the product here. Okay, and you can see here the third one we are getting the very high. So this here, so it depends on all reaction mechanism how it is. In first case you see, in second case middle, and in third case you can see here almost higher here. And how we can go, what does this show? So first middle, so what it shows the equilibrium now. So it shows the equilibrium nature between the intermediate and the reactants. Okay, so equilibrium between the intermediate and the reaction. That means how nicely the product what is formed is going back to form the reactant. So it depends on the equilibrium. So how we can understand from this energy profile diagram that whatever product is formed is going to form back with the reactants. Okay, so see here, so you can see here during this energy profile diagram. So that is, if this is less, so from reactant you can see, from reactant this is very less. Okay, and this intermediate is very less complete. Okay, the reactant intermediate is very less compared to the intermediate which is formed towards the product. Okay, so when this is happens in this type of, this is happen, that means the gap, the activated complex here in the to form the product here is large compared to the gap between the reactant and this activated complex. When this happens, so you can see here that is there is complete equilibrium established between the R and I. So in this case what happens, in this is a case there is complete equilibrium is established between R and the intermediate. Okay, R and the intermediate. But in some cases you can see here, so here no equilibrium is established between R and the intermediate. No, because of the same here, almost the same. There is no difference between the intermediate to that of the reactant and intermediate to that of the product. See here, almost the same is that. So here there is no equilibrium is meted out. So here there is no equilibrium between the R and the reactant. So reactant to product is formed, but product to reactant is little bit difficult here, because the equilibrium is not established in this case. But here you can see, since the energy gap between the reactant and this is slow, very small compared to the product, and the intermediate gap between the product, so this is high, and that's why you can see in this cases we can see the complete intermediate is obtained here. So any case we can see the reversibility of this reaction in case of such type of energy profile diagrams. But here we cannot obtain the equilibrium establishment between the reactant and the intermediates. There is no equilibrium is maintained, and that's why if I want to reverse the reaction, so it is very difficult for this this reaction. So but in this reaction, if I want to reverse, definitely, so since complete equilibrium is established from product to reactant, again from intermediate to reactant, I can do it. So this is how the general concept of the energy profile diagram in a big way we can understand for the elementary single step as well as the elementary two steps. Now you can see here, we can say the favorable of the reaction based on the delta G naught value. Is it at free energy, and always it should be negative, and we call it exergonic. Okay, exergonic reaction. So free energy, and the free energy of the product should be always less than the free energy of the reactant for a favorable reaction, and the delta G naught is given by delta H naught minus T into delta S naught. This is very few because delta T is always less than 100. So that's why this is very negligible part. So delta H naught is the main to show whether the reaction is endothermic or exothermic, and we can see here if delta naught is less than 0 it is endothermic, and delta naught is greater than 0 it is a exothermic. And depending on the value of delta G naught versus this here, delta G star is large here, but delta G naught is very less than 0. So such reaction is slow and favorable. So this reaction is slow and favorable because delta G star is large here, this is small, so that's why this is slow and favorable. In this case you can see here small delta G star, so gap between activated complex and the reactant is very small, as well as delta naught is less than 0, like here only. This reaction is very small, very fast and favorable, and finally you can see here. So you can see here reactant is here and product is above, like endothermic I said no in first startup here. So that's why here what happens now, delta G naught is greater than 0. So here delta G naught will be greater than 0 and delta G star is less here, small. So such reactions we call it as a small delta G star. Here small gap is there, so this is fast and unfavorable. So this is what fast and unfavorable. So like this based on the energy profile diagram we can explain the whole concept of the elementary reactions, how they take part, and how we can represent the favorable and unfavorable mode of the reactions. Hope you understood this. In the next class we'll go for taking the complexes octahedral and octahedral complexes and learn the reaction mechanism. Thank you.